Now we have Neville Wilson talking about boundary partitions in trees and libraries.
Thanks. And everything here is joint work with Rick Kenyon. All right, so I put this in to tie it in with the theme of most of the other talks in the conference. So this is extracted from Razumov and Stroganov's paper, and in it they look at the connections, the paths connecting the different boundary points of an alternating sign matrix. So here's some other connection events that you can look at.
Can you speak a bit louder? Or switch the device?
Well, the microphone's on, so I'll just speak louder.
Yeah.
All right, so in the upper left, we have here a spanning tree and a finite graph. It's a grid, and on the left and on the right, those are single nodes that are just happen to be very long and drawn as edges. And in the spanning tree, there's a path connecting the left side to the right side. And these very long vertices, we're going to view them as being distinguished, and we're going to number them 1 and 2. And Kirchhoff showed that the electrical resistance can be expressed in terms of the number of spanning trees divided by the number of forests in which there are 2 trees and 1 and 2 are in separate trees. Okay, so on the right here is the analogous event for percolation. So here all the bonds occur independently, and this is the probability that 1 and 2 are connected. It's given by Carty's formula. Ziff gave a version that's more suitable for, re-express this in terms of the aspect ratio R of a rectangle. And of course, Smirnov proved this crossing formula for slight percolation on a different lattice. Okay, so we're interested in these types of events, and so here's a different region. This one's a regular hexagon, and so here again, well, okay, so in this picture, the analogous question is clear. Each bond occurs independently with probability half still. So in the right picture, the question that we're looking at is if you look at a forest such that every tree contains at least one of the nodes, and you let every such forest occur with equal probability, what's the probability of seeing a particular connection topology? So in this particular case, there were 2 trees. One tree connects the boundary vertices 1 and 3. The other tree contains just 2 by itself. And so in this case, if we let the grid spacing tend to 0, the red light's on. Is that better? I see. Okay, so as the grid spacing goes to 0, the probability of seeing this connection topology tends to 2 over root 3 minus 1 in this particular case. And for any graph on 3 nodes, the probability of seeing this particular connection topology is given by this formula, where these lambdas are variables which I haven't explained yet. They're known as entries of the Dirichlet to Neumann matrix, and they can also be expressed in terms of the pairwise electrical resistance in the graph if you view it as an electric network. And I'll define these variables more later. But anyway, so this holds for any planar graph in which these nodes are on the outer face, and it's just that for this particular geometry, you can compute these lambdas and it tends to that value.
The
Yes?
number of trees fixed? I don't, or is that freely fluctuating? The number of trees.
Okay, so the number of trees is going to be anywhere between 1 and 3, and the reason is we insist that every tree contain at least one of the boundary nodes. Okay, so and the corresponding.
It was not totally clear that each big segment is a single node. I had this impression that people what you denote by a segment with the letter 1 is one node.
That's right.
Okay, so in computing the trees, this is the way.
Right.
I had the impression that this was, I don't know if I did a good observation.
Okay. Yeah, and so in percolation, the corresponding event for this geometry was computed by Dubida. Okay, so this is related to other work on understanding multiple strand networks. So this picture is taken from a paper of Duplantier and Soler, and so what they're looking at here is exponents associated with certain networks, and in this case, they're boundary vertices attached to the boundary, and the other vertices in the interior. So I'll say more about the connection, but this is more general in the sense that you can have these internal vertices, and also they consider a much wider class of models. But if we look at this sort of question, it's more precise because we're not simply looking at the limiting behavior. We're actually computing the function. Well, I'll say more about that later. Okay. So returning to Kirchhoff's formula for the electrical resistance in a graph. So this is, it works for any graph. It's not simply continuous graphs. And this particular graph has 3 spanning trees, which are shown there. And it has 5 two-tree forests in which 1 and 2 are separated. And so Kirchhoff's formula tells us that the electrical resistance, if each of these edges has unit conductance, is 5/3. And Kirchhoff also told us how to compute the number of these spanning trees. So if you take the adjacency matrix with minus signs, and you put the degrees of each vertex on the diagonal, strike out a row and column, take the determinant, and that gives the number of spanning trees. And if you strike out multiple rows and columns, that gives the number of spanning forests that are rooted at those rows and columns.
So you cannot, for the first strike, you're not permitted to take the 2 sides, one of the 2 sides that you want to find the resistance.
I'm sorry.
Well, you struck out 3 rows and columns.
Right.
But at first you struck only 1.
That's right.
To get the total number of spanning trees.
Right.
But so you're not permitted at the first instance to take 1 or 2.
Doesn't change.
It doesn't change. No, it doesn't change. That's right. It doesn't. So it's not a big deal. Okay.
Okay, so if we wanted to use Kirchhoff's theorem, we would strike out 2 rows and columns, because then that would give the number of spanning forests rooted at nodes 1 and 2. And it's just that in this example I showed with 3 being struck out. Okay, so these are the groves on that graph. So a grove is a spanning forest such that every tree contains at least one of the distinguished nodes, which are colored orange. So all of these are groves. This one's not a grove because it contains a cycle, and this one's not a grove because the tree containing vertex 4 doesn't contain one of the distinguished nodes. Okay, so Kirchhoff's formula gives a formula for the number of groves of type where 1 and 2 are separate, divided by the number of groves of type where 1 and 2 are together. And we're looking at what happens when there are more nodes. And in this case, the number of groves of type where 1 is separate and 2 and 3 are together, normalized in this way, is this linear combination of the pairwise resistances. And this actually works for any graph. And this formula also holds.
Will you explain where this comes from?
Yes.
And these formulas were not known before?
Well, I'm not sure. So the case with 3 nodes isn't so hard to work out using inclusion-exclusion, using the original case with 2 nodes. So that may well have been known. I don't think that any cases like with 4 nodes have been worked out. Okay, speaking of 4 nodes, so here's a graph with 4 nodes. And all the pairwise resistances are equal. But nonetheless, in this graph, the number of groves where 1 and 2 are connected and 3 and 4 are connected, but separate from each other, is 0. And here's another graph in which all the pairwise resistances are equal. But in this case, 1 and 2 can be connected, 3 and 4 can be connected, and yet these 2 connections are disconnected. And so that tells us that if we want to say anything about 4 nodes or more, we have to make additional assumptions. Okay.
Those graphs have the same pairwise resistances?
Yeah. So if you were to put suitable weights here, all the weights being equal, and say weight 1 up there, then all the pairwise resistances will be equal. Okay, so the assumption that we make is that the graphs are circular planar, which is to say that they can be embedded in the plane such that all the distinguished nodes are on a circle and everything else is inside the circle. So these 2 graphs are circular planar. This one from the previous slide is planar but not circular planar.
What does circular planar really mean?
What does it really mean? It means that the graph can be embedded in the plane so that, well, furthermore, it's embedded inside the disk so that all the distinguished nodes are on the
distinguished vertices have to be at the circle.
on the circle, right?
It's planar embedding in the disk.
Right. Okay, and since we're looking at partitions and the graph happens to be planar, that tells us that any partition that we see is going to be non-crossing. So we'll never see this in a circular planar graph. And of course, the number of these things is given by the nth Catalan number. These are the number of groves of the different types, and we want to be able to compute these. Okay, so if you take the probability of seeing a particular connection topology and divide by the probability that a random grove happens to be a tree, this is a polynomial in the pairwise resistances between the nodes. And if we take this other normalization where we divide by the probability that all the nodes are separate, this is a polynomial in these variables L, which I haven't really defined yet, but will soon. Okay, so this is another example of groves which came up in enumerative combinatorics of Carroll and Spire, and also Peterson and Spire, but I'm not going to say any more about that. And so what I'm saying can be specialized to study multi-chordal SLE, which at this point there's been a lot of work on, and maybe I won't say much more about that. And I'll just return to groves. So this is a uniformly random grove. This one has 4 trees. 1 is by itself, 2, 7, and 8 are together. 3, 4, and 5 are together, and 6 is by itself. Okay, so this is a circular planar graph with 4 nodes, and the probability of seeing this particular connection topology is given by this quantity in the scaling limit. What?
What is this number?
Okay, so if you have this geometry and you ask for the probability that 1 is by itself, that 3 and 4 are connected, and that 2 is by itself, this converges to this number.
Do you know how to relate these numbers on a given geometry to another geometry which is topologically the same but deformed by some conformal map? Like in counting formulas.
Yeah, okay, so I mean, if you had some other domain and you took this geometry and mapped it to that, then you would have the same limiting probabilities. If you had some other geometry, then you'd have to compute these L's and then plug it into the formula.
Question.
Yeah?
And here you have some of these very big vertices.
Right.
Does it make a difference?
No, because the formulas work for any finite graph, even if some of the vertices are very big.
Just means that you identify some as random that we see here.
Right.
But this number refers to taking a big square grid, identifying half of the vertices on each edge as one vertex, and then taking the limit as the grid gets infinitely large.
Right.
But then when you do a conformal transform, how do you specify this length? I mean, the 3 and 4 being of equal length. What happens to the continuity? You said it was invariant.
Yeah, well, I mean, if you take some conformal map, then, I mean, what happens to them would
Also,
depend
you
on the...
start with the square with this length, and then you conformally back.
Right.
Somehow the 8 point goes somewhere and you keep the ordering, something like that.
That's right. Okay, so, I mean, you wouldn't have to have this particular geometry. You could have some other geometry, and somehow the problem boils down to computing these L's, which are the response matrix. And it just so happens that in this nice simple geometry, it's easy to compute the L's. And if you plug it into the general formula, this is the number that you get.
One
Yeah.
vertex was 359 degrees of the boundary circle,
Yeah?
and the other 3 vertices each just get 1/3 of a degree. Would it be the same answer?
No.
Well, there is some transformation of the square onto itself, such that there are these 8 points go somewhere, and the lengths are somehow fine-tuned in such a way that they get the same answer, something like that.
Yeah, I mean, if you picked all the lengths in a suitable way, then that's correct. But I don't think you're going to get the 359 degrees and the third of a degree.
That would be enough.
Okay. So one reason for looking at that particular graph is it's connected through work of Lawler, Schramm, and Werner to the SLE8 process. And this would tell us the probability that these nodes are connected in a certain way. So here's a different graph. So this one has 16 nodes. It has these very long nodes and these very short nodes. So the long nodes are conditioned to be in singleton components. The trees containing them contain no other nodes. And these very short nodes are conditioned to be in doubleton components. So the tree containing them contains exactly one other small node.
So you cannot understand what you said. Can you repeat?
Okay, so these large nodes are conditioned to be in a tree containing exactly one node, and these small nodes are conditioned to be in a tree containing exactly two nodes. And so this establishes a pairing between the small nodes, and this pairing has the property that if you were to fix the paths, fix all but one of the paths, then the distribution of the remaining path is distributed according to a loop erased random walk in the restricted domain with wired boundary. Okay, so in this particular case, the probability of this pairing is this number.
So what is this number coming from?
What is it?
The probability again, or what?
So for this pairing, right?
Right, so if you condition on a pairing of this type, what's the probability that 2 is connected to 3, 1 is connected to 4, that 7 and 8 are connected, and that 5 and 6 are connected?
And did you choose this boundary condition somehow because this is a good one for having conformal invariance? Because there is also the other natural one in which you just have the extra nodes and no special contracted nodes on these half edges, in which the blue, green, and so on, they fill all the lattices. There are no gray trees in a sense.
Yeah, okay, so there are lots of boundary conditions that you can look at. And
But
the reason that we used this one in this example is because from the work of Lawler, Schramm, and Werner, these paths are related to SLE2, and to us that seemed interesting.
So this is the one which is conformal invariant, and the other one would have had the bad boundary conditions.
No, this one is also conformally invariant.
So both would be. Oh, no. Well, this one is not with fixed starting points, however, the previous one. Because the starting point was somewhere on the half edge. So this is the first one you're showing us in which you already know exactly where you start from.
I'm not sure what you're saying.
Which just means that in this case, some of the nodes are not a whole bunch of nodes of the square contracted. Some of the nodes are individual nodes of the square.
That's right.
Which is what you want in SLE.
For SLE2.
Not necessarily.
Not necessarily, but for the
So
easiest
well,
flower
everything
row.
is fine.
Okay, so anyway, these were just some interesting examples, and I'm going to leave these examples behind and work on general graphs. Before doing that, I have another example of boundary connections that we're interested in, and this comes from the double dimer model, which we saw examples of in the previous talk, except that in our case, we have to assume that the graph is planar, and we also assume that it's bipartite. So this is the double dimer configuration with defects. So we have these loops, we have these doubled edges, and we also have special nodes which have degree 1. And from these nodes, there are paths connecting them to each other.
So the defects are these special vertices, these edges in between, they are two loop vectors. These edges, they are not defects. Or are they?
Which edges?
I mean, these singleton edges.
These? No, these are not defects. These,
They're two loop, right?
yeah, this is a two-cycle. There are two edges on top of each other.
So what precisely is the definition of the double diamond model?
You superimpose two.
So it's just two dimer configurations with any relation between them, or?
No, these are independent, but you notice that the graphs are slightly different. So like in this one, this graph has node 1, but in this graph, node 1 has been omitted.
But aside from the special nodes, a double dimer configuration is just the superposition of two independent dimer configurations on the same graph?
That's right. Or closely related graphs. Okay, so, and we're also interested in computing, yes?
So these special vertices, they can be considered as some boundary conditions for this double diamond.
That's right. Okay, and so we're also interested in computing the probabilities that when you take the superposition of these two dimer coverings, that the special nodes are paired off in a particular way. This way, 1 and 8, 3 and 4, 5, 2, and 7 and 6 were paired. And we want to be able to compute these. And of course, we're only going to see planar pairings. This one being an example of a non-planar pairing. And again, there's a Catalan number of these. Okay, so this is just a fun example that we did. So in this case, the graph in question is the upper half plane, or Z2 restricted to the upper half plane. And the defects where these paths start out at are evenly spaced and they alternate in color. And if you have infinitely many of these defects, you can ask, what's the pairing probabilities? Well, okay, they're all 0. But you can ask for certain marginals, like what's the probability that a given vertex is paired off to the adjacent one to the right? And this turns out to be 4 over pi squared.
Is jumping probability, for example, +3, +5 also?
Plus, okay, that's not going to happen because then 4 would be by itself.
Sorry? Well, this is +1, isn't it? Probably
Right.
the black one goes to +1.
Right.
There is a +3, +5, +7. You know all of them, or only
Yes.
+1?
So we know how to compute all the marginals, including those. Okay, so this is an example. This picture was taken from Schramm and Sheffield's paper. It shows the Gaussian free field with certain boundary conditions. And this is a contour line in this Gaussian free field, which...
At height 0 or at some other height?
Well, okay, so the left-hand side has one height, the right-hand side has a different height, and the contour line is in the middle. And what Strom and Sheffield proved is that if you look at this contour line, then in the limit this converges to SLE4. And the double dimer model paths are thought to converge to SLE4, but there's no proof. However, we can show that if you look at the connection probabilities, if you were to alternate the boundary multiple times in the discrete Gaussian free field and look at the connection probabilities, that these are exactly the same connection probabilities for the double dimer model with suitable boundary. Okay, so so at this point, we're going to return to trees, and I'm going to say a bit about where these formulas come from. And for dimers, there's a similar story, which I'm not going to have so much time to talk about. But anyway, so for trees, this is an example of one of the graphs that we saw before, and we're viewing this as an electric network. And probably everybody is familiar with the electrical resistance between two nodes. What you do is you apply a battery to the two nodes, you measure how much current flows, and the resistance is the reciprocal of that, assuming that you applied 1 volt. And it's symmetric. The resistance between 5 and 2 is the same as the resistance between 2 and 5. Which, by Kirchhoff's formula, was the probability that a spanning forest with the nodes 5 and 2 has 5 and 2 separate divided by the probability that 5 and 2 are together. Okay, so these L variables are given by the following. So L52 is given by the following experiment. You take your battery, apply 1 volt to node 5 and 0 volts to all the other nodes, and then you measure how much current flows into node 2. And it's not obvious from this definition, but these L's are also symmetric in the indices. And these L's are easily computable using linear algebra. So if you start out with the original Kirchhoff matrix and take what's known as the Schur complement. What? The Schur complement?
SCHUR. Yeah.
Okay, so anyway, I don't want to go into great detail about how to compute the Schur complement, but it is, well, it's algebra and it's not hard. And in the end, you end up with this matrix, which if you take the voltages at the terminal nodes, it gives you the currents. And this is why it's called the current response matrix. And because this matrix was symmetric and the Schur complement is given in this way, it follows that the L's are symmetric.
So lambda is L.
L is negative lambda. So all these lambdas, like lambda 1, 2, all these quantities are negative, and so we just found it convenient to define L 1, 2 to be the positive. Okay, so this is a different version of the matrix tree theorem. And I'm not sure how much I want to say about this. Well, okay, so let me just say that if you add an extra node, 0, with edges of weight epsilon going to all the other nodes, and you take the number of spanning trees of this graph and divide by 3 epsilon, that's also in the limit going to the number of spanning trees of the original graph. And this is can be expressed in this way. If you were to take the determinant of this matrix, that's another way of getting the number of spanning trees. Okay, so this matrix can be factored. This is an LU decomposition. Lambda epsilon is the surcomplement of this graph, this matrix. So it's given by this formula, and it's the original lambda with modified a little bit by these epsilons. And the upshot is that if you were to compute the probability of a tree divided by the probability of the uncrossing, which is what you get when all the nodes are disconnected, this is just the determinant of lambda prime, which is lambda with one row and one column struck out. Okay, so with that motivation, okay, so let's take a look at what the determinant of lambda prime is. So if we look at this graph, this is electrically equivalent to the original graph. So if you take these L's and you take a complete graph, take every edge and weight it by L of the two endpoints, this has the same response matrix as the original graph. And what the determinant of lambda prime is it gives a sum over all spanning forests, spanning trees of this graph, where for each spanning tree you associate a monomial, and for every edge from I to j you include a factor of Lij. So in this case the graph has 16 trees, so the polynomial has 16 terms, and each of these corresponds to a tree.
So the L's are just the inverses of the R's, is that correct?
No. So if the graph has two nodes, that's correct. If it has more than two nodes, then it's not true. But the L's and the R's are related by some simple linear algebra. So if you have the R's, you can get the L's, and vice versa. Okay. So with that motivation, we're going to define L of any partition to be the probability of seeing a grove with that partition type divided by the probability of seeing the uncrossing on the electrically equivalent complete graph with these weights. Okay, so L 1, 2, 3, 4 we saw before. L of 1, 2 together with, and also 3 and 4 together is just L1, 2, L3, 4, because there's only one forest with this connection type. L of 1, 2, 3, and then 4 separate is this polynomial, because there are 3 ways to pick a spanning tree in the nodes 1, 2, 3, and the node 4 doesn't do anything in this case. Okay, so on 4 nodes, in terms of these L sub taus, these are the grove connection probabilities. They always turn out to be a linear combination of the L sub taus, and we'll see why in a moment.
Go back for a second.
Yeah?
In the second line,
Yeah?
1, 4, and 3 are in the same block, but they're not treated symmetrically. That's because 1, 2, 3, 4 are cyclic around the boundary.
Right. Okay, so we can write down a matrix which tells us how to write these grove partition probabilities. So the rows of the matrix are indexed by the non-crossing partitions, and the columns are indexed by all partitions. And this matrix just summarizes these formulas. And the way to read it is if we want to know the probability that 1 and 4 are connected and that 2 and 3 are connected, then this probability is L of 1, 4, 2, 3 minus L of 1, 3, 2, 4. And we'll see where this matrix comes from in just a bit. So to explain this, we just quickly review a bilinear form on planar partitions. So here's a partition. 1 is by itself, 2, 7, and 8 are together, 3, 4, and 5 are together, and 6 is by itself. Here's another partition, which is given by this one. And if you glue them together, there's one cycle. And so this bilinear form is q to the 1. Here's another example. And in this case, there are 3 cycles, this outer one, this one, and that one. And so here the bilinear form is q cubed. This is a multiplication table. All right, so if everybody picks a different diagram here, they can count the number.
Go back for a second. I mean, you drew your partitions in this funny way with 2 lines rather than the usual way with just arcs.
Right.
But you could have defined this equally well in terms of the numbers of connected components that you get when you put together with ordinary arcs.
Right.
To back up even one more. No? Yes, well, no, this one.
Yeah.
What is the reason that you have the elementary arches also below 3, 5, and 7?
No, that's because it is not.
That's just a funny way of drawing it.
It's a reminiscence of the second part. It's a kind of having cut a single figure.
Oh, okay. You mean this is just graphical?
Yes, a rough cutting in a sense.
Oh.
It's a piece of the smaller one. If I were interpreting.
Right.
Okay, thank you.
Okay. So if everybody wants to pick a different entry of this multiplication table, count the number of arcs.
How would you figure out that everyone has a different one?
All right. Maybe 2 people pick the same. It doesn't matter. All right. So this is okay. So informally, we call this the meander matrix. More formally, this is known as the Gram matrix of the temporally Lieb algebra. And Cohen-Smolinski determined for which values of Q the matrix is singular. And DeFrancesco, Galinelli, and Gutierrez gave an explicit diagonalization of this matrix.
Cohen-Smolinski computed the determinant, right?
What?
Cohen-Smolinski computed the determinant.
No? Computed the zeros.
Only the zeros?
Yeah.
Okay.
Yeah,
that's I always had the impression that they computed the determinant.
This is the one bound factors.
Okay. Okay, so anyway, the key results that we need for our work is that it's non-singular when Q equals 2, and this is the relevant fact for the double dimer model, which is sort of related to the O2 model, which is why 2 is relevant. And if you were to divide by q and then take the limit q goes to 0, the other fact that we need is that this is non-singular. And the reason for that is for groves, this is kind of related to the O0 model, and so that's why 0 is relevant here.
Is it really the O0 model, or is it the zero-state Potts model?
0-state Potts, yeah.
And so then the other, the double dimer is related to O2, or is it related to two-state Potts?
It's related to O2.
Oh.
Well, I mean, it's not exactly O2 because you're allowed to have these doubled edges, but somehow it's quite similar to O2. What?
I mean, I'm confused whether Q. I'm confused whether Q is the Q of a Q state Potts model, or it's
No.
the end of
That's
an
a
O.
square root. That's a square root.
Ah.
So
Square root
Q
of
equals
Q.
2 here is 4.
Ah. So what? So the trees of Q equals 0, which I know, and the double dimer is related to Q equals 4 Potts. I see. Okay.
But it's probable that the Gram matrix for an irreducible representation of the EQ algebra has been also computed. So it would be a special case, this one. It's just a representation of the EQ algebra indexed by a partition which is a rectangle with 2 rows. And so more generally, you have Gram matrices for the representation, the irreducible representation of the EQ algebra.
Okay. So maybe we can talk more about that afterwards.
But I believe that the people computed the Gram matrix.
Okay. So going back to this bilinear form, so in the special case, when we divide by q and send q to 0, there's an alternative combinatorial characterization of this bilinear form. And what this other characterization is that if you take the partition sigma and tau and you glue them together, when you divide by q and send q to 0, you get 1 precisely when, if you take these two partitions glued together, you get a tree, and you get 0 if you get something that isn't a tree because it has, say, extra components.
Which one is tau and which one?
Well, it doesn't matter because they're symmetric. But if you like, sigma's on top and tau's on bottom.
Is it just another way of saying if you take the join of these two partitions in the partition lattice, then you have exactly one block?
Yeah, and furthermore, that there weren't any extra redundant joins. Okay. So we're going to let G sigma be the graph that you get by gluing the nodes together according to the partition sigma. And so G sigma of tree, we can compute this using the matrix tree theorem. You just glue the nodes together, you get a new graph, and use Kirchhoff's matrix tree theorem. Okay, so if you look at ZG sigma of the uncrossing, this is precisely the same as ZG of the uncrossing. And so this equation is essentially a tautology. So what it says here is that if you take any tree of type sigma, if you take any tree of type, any grove of type tau in the original graph, and if you were to glue together the nodes according to sigma, if the result is still a tree, then you would have counted it over here. And if the result is not a tree, then you would not have counted it over here. Okay, so this is just the tautology.
And we say pictorially that the description of the graph, how they are connected, can be thought as a link pattern on the outer boundary of the disk, and the tree probability can be described as a link pattern in the inner boundary of the disk, and the diagram in abstract that you showed us are really the diagrams that would happen in the statistical mechanics model in the picture, just on the line instead of the tree of the disk.
I'm not sure about the last sentence on the line rather than the disk, but I agree with the rest of what you said. By the way, nothing so far depends on planarity, so that'll come in a moment. Okay, so I'm just going to take this equation and re-express it in matrix vector notation. So these g's, that g vector is just the g of the sigmas for all the different choices of partition sigma. The z vector is these z taus for all the different choices of tau. And E is this extended graph matrix where tau is allowed to range over all the partitions and not just the non-crossing ones. And so that's just the same equation as above. Okay. Okay, but these g sigmas can be expressed as a polynomial in terms of the Lij's. And the reason for that is because we know how to compute these g sigmas. We just take the nodes, glue them together, and if you glue them together, what happens to the response matrix is that some of the rows get added to each other, some of the columns get added to each other, and then when you use the matrix tree theorem, in the end what you get is a polynomial in the Lij's. And so in particular it's determined by the Lij's. And so what that says is that we could do this precise same calculation on the electrically equivalent complete graph where all the edges have weights given by the Lij's. And this equation would still hold true. Okay, but for the electrically equivalent complete graph, these z sub taus are precisely the L sub taus. That was very conveniently defined. Okay, so these g's didn't care which graph they were computed on, the electrically equivalent complete graph or the original graph, and so we have this equation. And for planar graphs, the z's are 0 for the non-crossing partitions. And then using the fact that the meander matrix is invertible, you can multiply by the inverse on both sides. On the left side, it just drops out. And on the right side, you get you get a linear combination of the L taus.
This looks a little bit funny because you have still ET set.
Right.
Is ETL.
Right.
But those are rectangular matrices?
These are rectangular matrices.
And MT is precisely the square part. MT is the square part of ET.
Right.
It leaves out the crossing partitions.
Right. Okay, so this is just copying from the previous slide. And PT is defined to be MT inverse times ET. Now, MT inverse has all kinds of rational fractions in it. And so a priori it's not clear that MT inverse times ET is going to be, well, I mean, a priori you would think it would have rational fractions in it. But in fact, it's all integer valued. And the reason for that is there's an alternative way to compute P. Okay, so this is just recalling that the rows of this P matrix tell us how to compute the growth partition probabilities. And if you do some linear algebra, this shows how to interpret the columns. If you take any partition row and you take the bilinear form between row and the associated column, the tauth column, well, because it's bilinear, you can express it this way. This was the definition of the E matrix, and I'm sorry, the M matrix, and so this can be expressed this way, and then this collapses down to that. And so what this says is that the columns tell you how to re-express tau in terms of an equivalent linear combination of planar partitions. Okay, so Caracciolo, Socco and Sportiello are looking at something that's related, and I think that Andreas is going to.
No, I was just noticing that Caracciolo is a bit misspelled.
Oh, it is?
Double C single L, but that's the important is that Sportiello is misspelled.
Okay. All right. So anyway, so I'm going to say that this linear combination of partitions is equivalent to that linear combination of partitions. And what I mean by this equivalence is that if you take any partition, for example, row, and you take the inner product between row and the left-hand side, well, okay, so we could just work it out. If you take, okay, so if you glue 2 and 3 together, you're going to get 0 because 2 and 3 are already connected, and that wouldn't result in a tree. 2 and 3 are not connected, and so that gives a tree, so you get 1. 2 and 3 get glued, that's a tree, so you get 1. 2 and 3 are already connected, so you get 0. And so you have 2 on the left-hand side. And on the right-hand side, if you do a similar computation, you find that you also get 2. And for any choice of row, you find that the two sides are equivalent. Okay, so here's a fact. If you have any partition tau, which is expressible as a linear combination of planar partitions, and you join another part n, then tau with the new part n is also expressible as a linear combination. And the other thing you can do is if you take a particular index j and replace it with j comma n, and tau is this original linear combination of planar partitions, then tau with j replaced by jn is also a linear combination, the same linear combination, but you take all the j's and replace them with j comma n.
I'm sorry, where n is a new vertex?
N is a new vertex. Okay, so these last two rules are plausible, and they aren't too hard to check. And the fact is that if you take these rules, you can express any partition as an equivalent linear combination of planar partitions. And this is just going through an example of how to do it. And so what this shows is that, well, okay, if you apply these rules, the linear combination of planar partitions that you get is going to have only integer coefficients. And we saw before that that gives the characterization of the column of this P matrix. So, so using just these combinatorial rules, you can obtain the formulas for the growth probabilities.
But you don't have an explicit formula for the final result. You simply have an algorithm.
Well, it depends on what you mean by explicit.
product of these matrices.
What?
It was the product of these matrices.
Yes. Okay, and this is just explaining the induction of how you can convert any partition into a linear combination of planar partitions. These are just the growth probabilities on 4 nodes. These are special cases of a formula that was given by Curtis, Ingerman, and Morrow.
I'm sorry, Curtis, Ingerman, and Morrow, is that the formula for determinant of a partitioned matrix?
This is, okay, so there's chalk. I don't see any chalk.
On the blackboard.
Okay, so what they showed is if you have 2n nodes and the top 2 are paired and the next 2 are paired, you have like this parallel crossing. If you look at that partition, they show how to compute the normalized probability of seeing that. And using electric network duality, which I'm not going to go through in great detail, and a little bit of work, not too much work. This shows how you get the polynomials in terms of the pairwise electrical resistances. And this is, all right, this is the Curtis-Ingerman-Morrow formula. If you have pairings of this sort, you get a determinant of the L matrix. And this is somehow analogous to, but slightly different than Foman's formula. Since in Foman's work, he used different variables besides the L's and a different normalization. And I'll just mention one other fact, 2 other facts. This is one of them. Okay, so we saw in the conference 2 weeks ago that there was a Pfaffian formula associated with 3 regular hypergraphs. That was in Grasbaum's talk. And so this is, as far as we know, a completely different Pfaffian formula. And this one is associated with groves. And this is what you would get if you have a tripartite pairing where each color has to be paired off with a different color. This is a slight generalization of the previous formula. This one, there are essentially only 2 colors, red and green. And you can see that this formula specializes to the other one. If you were to eliminate the blue color, there aren't any blue vertices. That goes away. And if you have the Pfaffian of this submatrix, you get the determinant of that piece of it. And you can get this formula because the combinatorial rules are sufficiently explicit that you can work it out. And the other fact I'm going to mention is that for double dimer pairings, there's a similar story which uses Castellani matrices instead of the matrix tree theorem. You also get polynomials in terms of a different set of variables. And each of those polynomials turns out to be a special case of a grove polynomial. And I'll stop here.
Is there any more questions?
May I make a comment? Actually, that's a bit on the bridge between this talk and the previous one. When Professor Di Francesco asked us this question about the surface with a boundary, I think I misunderstood at the beginning. Maybe you were meaning that given a boundary, you can work out with the method the dimer partition function in which you can have an arbitrary number of monomers on the vertices which lie on the boundary. Because monomers are like I do what I want with groves on the boundary. So boundary in the surface is like allowing for monomer terms on a subset of vertices corresponding to that.
Or fixing the position of the
Which is an extra term in the Hamiltonian. Original one was only dimers.
Questions? So let's go to 3 on resuming